Ladies and gentlemen, my name is Joe Decuir. I worked at Atari from December of 1975 through June of 1979. I had the great privilege to get to work on Atari 2600, both the hardware design and cartridges. And I got to work on the design and development of our second system, which we call the PCS, as in Personal Computer System, or the Atari 400 and 800, etc., etc., etc. I have a bunch of other credentials. None of them matter at this point. But my email address is actually there, and I do sometimes take tech support calls. And I like questions. I like when people want to know stuff because, first of all, if somebody's brave enough to ask the question, usually part of the rest of the audience also cares and want to try it out. And that means you're more likely to remember what it is I tell you. When I give talks, and I give a lot of talks around the world, I try to do four things. I try to explain what this thing is, how does it work, because many of you are engineers, what's it good for, and where do I learn more. This talk, for example, will end with a bunch of resources, things I recommend. Some of the books are here. Come on. I need my reading glasses to tell where the advance button is. Here we are. Okay. Here's what I want to talk about. First of all, we had just built a successful system. What did we learn from this? What was the competitive landscape in the late 1970s? How did we decide what product we were targeting, or what market we were targeting? Has anyone ever heard of a good definition of marketing? Because I'll tell you one. Good marketing are the people who understand what it is you're selling, who's buying it, and why are they buying it from you. If you interview for a job somewhere and they don't understand real marketing, go get a different job. How we decided the hardware features, how we decided the software features. We ported other games to this thing. We had at least one fantastic original game developed for this system. And I'll talk a little bit about the development ecosystem and what lessons we learned from this process, which animated the next system, which became the Amiga. I hit the right button. Okay, we had a success, which was the video computer system, aka 2600. Is there anybody here who failed to notice the Atari Age displays right in front as you walked in the door? I think none of you. In fact, I would ask a different question. Is there anyone in this room who has never played a game on an Atari 2600 before? That's what I thought. It's sort of hard to find people. In fact, it's hard to find engineers in this country who grew up and didn't have one as children. What?
My 2.5-year-old son, his first game was ARC Battle. There you go.
His first game, when he was 6 years old, he came home from first grade. He said, I said, what did you do today? He said, we learned to play handball. Really? And I went in my garage and I pulled out an Atari 2600 and I pulled out Video Olympics, which I had helped write. And I put it in front of him. He learned it instantly. It had handicap switches on it. The first 2 or 3 times I played with him, I was handicapped and he was not. Pretty quickly, we were playing even. Okay? He's 6. I'm 38. Right? And at the end of it, I said, what do you think of all this? He said, Dad, this is hecka fresh. And I realized at that point that I was on the other side of a generational divide because I had no idea what he was saying. But from his attitude, I knew he was happy. Okay, so we had a good idea, which we executed well. The title of the book that I want to write is called The Second System Effect, because it's about one of the hazards that applies in software engineering. If you keep a very tight idea and you don't deviate from it, and you don't put lots of bells and whistles in it, and you just do what you originally planned to do, you might succeed. And if you do succeed, then you'll turn around and think, what would we like to have done that we didn't get to do? And this is the second system. I've had a couple of chats today with people about how, gosh, I wish we bought a bigger processor with more memory going to the cartridge and put read, write, and phase 2 in the cartridge, and we could have done a lot of other things. There are some amazing things out there that I wish we had the foresight, at least in retrospect, we wish they had the foresight to do. But in fact, we were trying to we thought this system would have a 3-year, 4-year lifespan, starting from 1977. We thought that pretty soon we needed to replace it with something that was much more powerful because the industry was moving so fast. And, you know, so we resisted temptations to do our second system on our first system. And then we came around and did our real second system, which is what this is all about. So, our first marketing concept was simple. We want to be able to do good, great, much better video games. And we wanted to do home computers. We were competing, the Apple II came out at the same time in 1977. A couple of references here. There is a book that is a really good technical history of this machine, and it is called Racing the Beam. If anybody here who likes 2600 and has not read this, they should get it and they should read it. It explains, for example, as a chapter that explains David Crane's Pitball game. If you ever wanted to know, you want this thing. All right, and also, there's a couple of guys named Kurt and Marty who wrote this book, which is, in my opinion, the best social history of Atari at the time. Anyway, one of the things that was crucial in this product that we built was that the 6502 was architecturally fast enough that that is a line-by-line machine, not a screen map. Because enough memory for an 80 by 80 screen map, which is what the Channel F has, would have been a tremendous amount of money at that time in history and would have been really slow to manipulate, really slow to get it to do anything. Instead, we built a system where the processor was fast enough to load the things line by line as it flew down the screen. And if you go to the discussions later about how, or tomorrow, about how people build games for these things, that's what you'll learn. It was pretty arcane, actually. But it was cost effective in 1977, when our bill of materials for the first product was about $65 for something that retailed for $200. And this is in 1977, so compared to today, those are much larger numbers. So that's what it looked like. I'm sure that you're all familiar with it by now. And that's Combat, which we shipped with the product. I worked on Combat. I built the display engine. A guy named Larry Wagner did a much better job than I did of finishing and making it more fun. I was a hardware guy. I liked getting hardware things to work. And a system diagram of the thing is, you have a TV display. It's taking modulated video signals in. So it's got a modulator in it, which means it's subject to severe FCC regulations from the time. It has a chip that does audio and video I/O, which is the TIA chip. It has a plug-in cartridge as a CPU system, and it has more I/O for those controllers and whatnot. So that's the old system. Here's what the system diagram looks like, and that's coded out of one of my notebooks. It's over here. Never mind. Anyway, that's what the inside of it looks like. And those confidential notices were from a time when it was confidential. But it's not anymore. Okay, so what did we learn from this? Well, we thought we needed to build an ecosystem of support because we didn't know which video game was going to be the most successful. And people will spend some money on the console, and then they're going to want to invest in the console that's more likely to play the games, the applications. People buy these things not to have a console. They buy these things to have a game that they want that satisfies them in some way. So we thought the lesson that we learned was we should make it possible for other people to write games for this. That was before the guys from Activision and the guys from Magic left and started competing with Atari, and they got very upset about this. But we weren't afraid of them yet. We thought we needed to build a viable ecosystem, and that would be the way to do it. There's a guy named Bill Joy who I knew in graduate school at Berkeley after I worked at Atari, and he said, you should design your company on the principle that not all of the smart people in the world work for you. And that's what, you know, like them or not, the Wintel people who built the PC industry built it that way. They built it so that a lot of other people could come in and add value and build an ecosystem on top of a chip and an operating system. So we wanted to allow for self-development, and we thought the effect of that would be more development would make our platform more popular, which would make it more popular, you know, a better system. Okay, we wanted for looking at what people actually did. So we hired a handful of programmers, including David Crane, and they managed to write some code that really blew our doors off. They did things that went way beyond what we expected them to be able to do. In fact, here we are at a conference. Let's see, this thing came out in 1977. It's 36 years later, and here's a conference, and people are still doing new development for that platform. People could do a lot more for it than we expected because they were able to follow the beam down the screen and make changes on the fly. So a lesson that we drew from this process is that level of flexibility is really important. Even if we make a system that where the hardware does more, we should allow the software to be able to jump in and do things and do more, and not knowing what they were going to ask for. But we knew that in the next system, we would finally be able to afford a screen display. The 2600 has basically a hardware line, and the processor follows it down. In all the subsequent machines, there is a bit map or a character map or both. And we knew we'd be able to afford one. That's what we got out of that so far. But we were going to need to be able to move it efficiently. If you look at the way the Channel F plays, it's very slow. And if you look at a lot of the other games for machines of that period, their operation is pretty slow. There's a lot they can't do. And so we wanted to be able to use memory efficiently and to make other things happen efficiently. And I'll get to those. So we had two kinds of competition in 1977. We had video game consoles. The ColecoVision was coming along. The Mattel was working on the Intellivision, which was a bitmap. And there was the Fairchild Channel F, which was sort of the first thing that took consoles. It beat us by a few months, but it was so slow that it was, in my opinion, unplayable. In personal computers, the S100 machines had come out. Anybody ever seen, you know, the original stuff that Bill Gates wrote software for? The, IMSIs and the Altairs and all those things, right? The Apple II came out in 1977, and we knew a lot about the Apple II. I was at, they had this movie about Steve Jobs recently. Anybody seen it? Really? All right. In that movie, they have two events that I was at. They had the first Homebrew Computer Club meeting where Steve Wozniak brought the Apple I, and I was there. It was on Stanford campus. And a year later, they had the first West Coast Computer Fair with the Apple II booth. I was at both of those places. So we were aware of what they did. The Commodore PET was another machine that used the same 6502 processor. It was an integrated machine, had a monitor built in, a cassette drive built in. And there was a Radio Shack TRS-80, which was an 8080 machine with a separate keyboard, main unit, and monitor, all bundled together. That was our main competition at that time in history. So the Apple II looks like this. I want to point out some things here. The Apple II, this is it driving not a regular TV, but driving a monitor. The original Apple II was shipped with a monitor output and not a modulated RF, output. So they could dodge a lot of really tough FCC radiation requirements, so they could have slots. And slots made it a whole lot cheaper to talk to external floppy drives than having to wrap things up all tightly, as I'll explain. So it was a character-oriented machine. It could do extremely simple games. And Steve Wozniak did a breakout implementation on it, but by no stretch of imagination was the Apple a moving graphics, arcade quality machine. But we at Atari thought that our next machine had to be able to do circa 1977 arcade stuff, which we did. So our concept was that the best home computer would also have to play great games. This dichotomy pulled us constantly in different directions. What does it take to make a next generation game machine? What does it take to make a useful home productivity computer? So we brought out two machines which were, from a software standpoint, identical internally, but physically different. We brought out the Atari 800, and this is an example of the original 800. You can feel how much it weighs later. And we brought out the Atari 400. That was packaged as a full computer with a real keyboard and etc. and room for more memory to be added on. And the Atari 400 was packaged as a game machine with a very simple keyboard. We realized Star Raiders was such a great game that we realized we had to have a keyboard of some kind built into it because it was killer. And because of that, we put in the simple keyboard, and we packaged it all up, and that was our game player that can also be a computer. And the differences is the 400 had, tiny keyboard versus a real one. It had fixed RAM versus expandable RAM. So I have a picture somewhere in here. I had a picture. There we are. That's what a 400, looked like. Okay, so what are the applications for a game player console? We wanted to be able to, fundamentally we want to be able to port the best current coin-op video games home. That was the original concept of the 2600, was to bring the best games from that period home. We wanted to be able to have real bitmaps with multiple colors. We wanted to have character maps for repetitive detail. That's how you save a lot of RAM space and be able to change what's happening rapidly. We wanted to have even more moving objects because there could be a lot more things going on. And we wanted to be able to add playfield motion in 2 dimensions. Now, all of you today have seen displays where the background moves up, down, sideways quite quickly, smoothly. That was invented for this machine in 1977. This was the first machine that could do that. Therefore, what does the console need? We wanted to have a screen map with resolution higher than 40 by 24. Duh. I mean, 40 lines times 24 lines is 120 bytes. Now, remember that the 2600 only had 128 bytes total in the entire system. And we wanted to do a little better than that. But we wanted to display a lot more. So our original design goal said that we're going to have a screen display that it has to have at least 4K bytes. And we shipped it with 8K bytes or more because we discovered that we could buy 16K bit defective parts where half of it didn't work and the other half did. And we can get them for a lot cheaper. So we get 8 of those and you got 8K bytes of RAM. So the original machines came with 8K bytes. We invented graphics character maps to use the same hardware that you would use for, alphanumeric characters for displays instead. And these character maps, instead of being, let's say, an 8x8 rectangle, they would be a 4x8 rectangle with 2 bits per character, so they'd be colored. So you can have 4 different colors in it. And if you're building something with a lot of repetitiveness in it, you can build those things and move them and change them quickly. We added the ability to scroll in 2 dimensions. So there's hardware support for it. It's a long discussion, so it's going to go in the book. It's not going to go here. But that's where we invented that ability. We also extended the ability to do sprites, as TI calls them. So in the 2600, it had a pair of 8-bit sprites, which could be replicated. And it had 3 single-bit sprites turned on or off. This thing had 4 sprites that were each 8-bit wide but could be very long, and 4 more 2-bit sprites, which could all be moved independently. And we had hardware collision detection for all these things. And we designed the structure so that there was structure to the display, what was being done in the bitmap. And so you could change scrolling somewhere, you could get a software interrupt somewhere to come in and change some colors or shift something, or we didn't know what all the programmers were going to do. The programmers had taught us with a VCS that they were a lot cleverer than we realized. And so we, the hardware people, thought by putting a lot of general tools at their disposal that they'd make up new stuff. And they did. So, one of the 3 chips in this machine is called the ANTIC, alphanumeric TV interface device. And it is a simple parallel processor. It only has a small number of instructions. The first instruction is, what's the graphics mode going to be like for the next line to several lines? One of them is there an interrupt? And there are bits that turn on hardware and vertical and horizontal scrolling. All right. So one of the modes is simple, as high as resolution as I can go, 320 bits across by so many lines vertical. And some of them are really simple, and some of them are in between. For bitmap graphics and for character graphics. So yes, this is a good time for me to try to demonstrate some of these things. All right. That was it. Except that I don't want. Okay. Ready. So, we constrained ourselves to home television sets. That means we couldn't put 80 characters across the screen. And at best, we could reliably do 40. So, this is the basic display. And let's see if I do, I don't even remember which one I want to try, but let's try that one. And let's say plot 0, 0. Did anything show up? No. Oh, color one. I think I'm going to back off of some of this. The important point is I can put up something that's 320 by 192. I can put up something that's 80 by 40. I can put up something that's 40 by 20 with different amounts of color. And I can not only do that, this is a special case where I put a little text window at the bottom, and this is all the same kind of display. This displayless processor can change mode on a line-by-line basis. So I could put this line up at the top I could put an area of a certain resolution, another area of a different kind of resolution on the same screen, pretty arbitrarily. Because, again, the programmers had proven themselves to be so smart that we had no idea what they were going to think up next. So we just put tools in front of them and let them try it out. Whoa. Bingo. Okay. So, yeah, I should have practiced these demos more. Here's what the 400 looked like. This is the system diagram of the inside of it. It has a 6502 full one. It has the Antic, which is the DMA engine. And as a side effect, it also does memory refresh. How many of you remember what dynamic memory is? I don't think they ship it anymore, but we used to need to refresh things like that. Right. We had the television GTIA, or different version of the TIA, which is what the graphics went into after it had been fetched out of memory by Antic, and then played to a TV with sound and pictures. And it, we had another chip called the Pokey, which scanned the keyboard, it scanned the paddles, and it talked SIO to the external stuff. We had an extra PIA for all the rest of the ports. And we could put in the original design, we put in, this is under a whole lot of shielding. Left side cartridge, right side cartridge. This was expensive to build. Processor under here, original memory, 2 expansion memory cards. You could plug in a third one. And we were trying to keep people's hands off of those connectors because we figured correctly that they were going to have a lot of trouble if they were exchanging them themselves. Anyway, this is the original machine. We shipped it. And yes, OSR, RAM, user RAM, left card, yep, okay. Why do people buy computers? I often think to myself, because I worked on a lot of computers for a long time after I worked on this, what are the applications that cause people to want to buy a computer? And I was in a store just 2 days ago trying to help some lady decide which notebook computer to buy, and I thought, these things must be really valuable because people put up with an awful lot of grief to be able to get these things to work. At that time in history, the biggest 4 applications for personal productivity were word processing, replacing a typewriter, and the whiteout that we all used to use way back when, in case we made a mistake. Spreadsheets. Anybody remember VisiCalc? It was the killer application for the Apple II. I know the guy who wrote it. Basic programming, write your own stuff, and communications. At that time in history, it wasn't called the internet at all. There was an ARPANET, of course. There were a bunch of BBSs that you could call into. So calling into a BBS and being able to trade email with people was a big deal at those times, right? Those were the biggest things that you could do at the time. What does a computer need as distinct from a game console? Well, first of all, it needs a character display, and I showed you something that was putting up a bunch of characters across. And because we were sticking with TVs, that means we couldn't display 80 characters. We could have 40. We had to have enough RAM for the applications, and we used, like I say, SRAM. So we had refresh cycles. We needed mass storage on some kind of diskette. I was always jealous that Wozniak had slots and I didn't. So we ended up with external floppy drives that looked like this. That weighs a large fraction of what that weighs. And we needed printer ports. And we need serial communication. So we built this thing called the Atari 850. It hangs off the serial bus. It has a printer port on it for the Centronics printers of that period. And it has 4 serial ports on the back for modems and any other thing that we might want to control. All right? So here's an example of what that system looked like at the time. Driving a TV display with a 410 cassette that almost no one used, an 820 printer, and an 810 floppy drive, big brick. I was happy a couple years later. In the early 80s, we brought out the 1027, which was a full 80-column printer instead of the little 40-column printer things. This one also hangs off of the serial bus. Here's what that machine on the end, this is what the inside of it looked like. Obviously, real keyboard, obviously a whole lot of circuitry on the side for power conversion and switch processing and whatnot. And then the main board, which had, as you can see over here on the far left, there's the processor board, fully populated with memory, OS memory, 2 cartridge slots, a bunch of I/O devices down in the bottom center to talk to the keyboard and to talk to all of those controllers. That's the inside of that thing. Does that look cost effective to build to you? I don't think so. Here's what a system diagram would look like. Obviously, we could have the processor and a connection to a monitor, modulated or not. We could talk on the serial bus. Here's the serial bus connector to external peripheral devices. And those peripheral devices in turn can talk to things like modems and 80-column printers and whatnot. So yeah, a fair bit of change when you got done. The external I/O requirements were problems. We loved that the Apple II had slots, which made I/O expansion easy. How they got the slots is they didn't have to have a TV RF modulator in the box. The FCC would have killed them if they had tried. So they had a regular monitor out, and a little company called M&R Enterprises sold the Apple II to TV adapter. So you could buy it at the Apple store, but you couldn't buy it from Apple. And so for several years, Apple avoided the attention of the FCC. What happened afterwards is a story I will not get into here. But Wozniak, who is a fantastic designer, did a great job of taking the complexity out of driving a floppy drive and moving it into 6502 firmware. So his manufactured cost for an extra disk drive was probably a third of what it cost to build one of these, because this thing has another 6502 and more memory, ROM and RAM, and I/O to talk to the floppy controller, and then talk on the serial bus to the rest of the system. This thing here has another 6502 and some ROM and some RAM and some I/O devices to talk to all these ports. It'd be much nicer to have a very simple little card to plug into the back of an Apple II. So, yeah, we wished. So we had this new problem. We're stuck. Given the decision that we had to be able to drive a real TV set, we still had to constrain all the fast I/O. So this thing has this. It's all worn away. It has all these covers. There's, this aluminum casting. I don't know if you can tell, but that's about 2 millimeters thick. That's why there's a reason they call this the tank. One could actually drive a car over this, and the electronics would still work, although the car might do bad things to the keyboard. Anyway, and there's an interlock so that this thing will not even turn on unless these things are closed. So, given that we were stuck, and at that time in history, the RF requirements were very severe, because we connect to a little thing on the back of the TV set, which was generating RF. And that means it's not far away from something that goes to an antenna, which is, if you all remember, before cable, we had antennas. That means we could connect to something that could broadcast our stuff to other neighbors. And they were very tight about what they would allow. The 2600 also has one of those thick castings, but it didn't need peripherals. It was a small victory for us when the FCC tried a bunch of different cartridges in the 2600, and it didn't matter what was plugged in on the connectors, as controllers. So we didn't have to recertify each cartridge with each controller. Can you imagine how much fun that would have been? So how do we expand the system? Well, so we put expansion inside, as I just demonstrated. But then we had to invent the SIO bus to talk to these external smart systems. We set it to 19.2 kilobits per second because that was quiet enough that the FCC, testing couldn't tell that it was running or not. It was that slow. But it was still fast enough for external external floppies. At the time, their transfer rate was so slow that it was okay. But they rapidly went past that. It was certainly fast enough for a printer. It was certainly fast enough for any of the modems that we were imagining at the time. It was completely inadequate for hard disk drives, but those cost hideous amounts of money in 1977, so that didn't happen for a few more years. I think the IBM XT, which is a PC with a built-in hard drive, came out in 83 or 84. And even a 10 megabyte hard drive was, several $100s as a component. So we weren't worried about those yet. We figured we'd have invented something else by then. Little did we know. So the decision to use home TVs and to support external computer I/O drove a lot of cost into a complete system. So, as I said, all of these things have separate processors in them. A complete useful system, one that would support all those applications, was too expensive to be competitive with the Apple II. Bottom line. You guys could ask me questions, but you haven't yet. Okay, that's what that looks like. You've seen it.
You're doing too good talking. Your son told me you do a great job talking.
Okay.
Okay, here's one. Was the second cartridge slot ever used?
The only knowledge I have of it ever being used was in the development world. People would build a prom burner that would fit in the second slot. I happen to have one. So it's a little cartridge, plugs in, and has a little socket on the top, and you could put it in a prom, and it would take some image that you generated and drive it to that second slot. That's it.
What was the intention of the second slot?
The intention was we were imagining families of software where there would be a basic piece of some kind, and then you would plug in second cartridges which were extensions of the first system. And that they would be cartridge-based rather than loaded into RAM, because at that time in history, RAM was really expensive. Like I say, the original machine had 8K bytes. You could fully expand it to 48K at the time with 3 different cards. The Apple II came with a bunch of chip slots. If you would usually pay if you were a hobbyist, you'd put your own chips in to expand your Apple II, but usually you'd pay somebody at the company that sold it to you to put in the chips and not screw them up and make sure it still worked before they gave it back to you, right? Once you've made the transition to having a lot of RAM and cheap, not expensive floppies, then distributing software on floppies is the way to go. But we were imagining relatively unsophisticated people operating the system. We wanted to make sure that they could handle it. We figured they could handle, for example, we had basic cartridge, right? What if somebody plugged in a cartridge which is a whole bunch of basic programs? That could fit in the right slot. right?
Could you have done like a high score cartridge on the right slot when games have battery in them?
Yeah, we could, because there's power in the cartridges. Yes, if you wanted. Non-volatile memory was also incredibly expensive at that time in history. Anyway, here briefly are the 13 pins on these things here. And by the way, these things were designed so that one machine is the source, and then it daisy chains out. So there's no Ethernet T's, and you don't need boxes like that to get connectivity. You just go in and go out. It's only 19.2, so it's not really a signal propagation problem. So clock input and output. Data input, single-ended, ground, data output, so it was a full duplex system. Motor control, only for the cassette. There was a proceed, which is basically, I'm ready to receive. 5 volts and 12 volts, audio input from the cassette, interrupts from a PC, so one of these wanted to ask for attention, it could generate an interrupt, come and service me please. And command line, that means the PC says, I'm going to tell you something, so you should all pay attention. I'm going to send out a command. I'll explain a lot more of it in the book. Questions about that before I proceed? Failing hearing none. Okay. So the system software. We accepted the 2600 has no software in it, right? You know, you turn it on, you just get vertical displays because that's all it can do. There is no BIOS. There's nothing in there. But this thing, we accepted it was going to have a lot of functions built into it. You know, obviously there's stuff like keyboards. We developed a BIOS, an input-output system. These things were brand new inventions at the time. Luckily, nobody sued us over those. All the essential internal I/O is abstracted via I/O control blocks. You know, get a character, put a character, this, that, and the other thing. They were all abstracted there. So the basic operating system in this thing, without BASIC running, will come up and will enable, the keyboard will be set up as device gate, and it'll set up S as the device screen, and it will just connect them together. And it'll run an extremely simple operation. Sit there and type stuff, and it's basically memo pad. That's all that thing will do. But it'll do something, and it was all abstracted. So you plug in the basic cartridge, it connects itself to the keyboard, it connects its output to the display. It also has an editor module that you talk to. If you plug in these guys, there'll be the D device, the R device for RS-232, there'll be a P device for a printer, and so on. Yes. The original BIOS, it was 8K for the BIOS itself, and then we took the floating point math package, thinking that other cartridges might use it, and put that in. So the original OS was 10K, but it was 8K plus 2. The rest of the system was on the disk operating system, and that got loaded in to RAM if you plugged in a disk, right? So what did we actually ship for personal productivity? We shipped Atari Writer, so there was something you can replace your typewriter with. Software Arts produced VisiCalc, compatible with the Apple II version. Synapse bundled a set of tools, SynCalc, SynTrend, SynFile. Broderbund produced Print Shop, which is really nice graphic stuff. Atari itself shipped Telelink as a terminal emulator for BBS access. We did a bunch of educational stuff. Atari produced an educational system cartridge, which accepted a lot of material on the cassette. We also produced a Pilot linking link, programming cartridge and toolkit. Anybody ever hear of Pilot? Right, those of us who are old-timers. And Fisher-Price produced something called linking logic. So we had a lot of the right kinds of functions there. The system, in retrospect, was too expensive, but at least it worked. Ported games. So I have 1, 2, 3, 4, 5, 6, 7. I have 7. Okay, who wants to see one of those? 2 minutes? I'm in big trouble.
No.
Choose one.
Galaxian.
Galaxian. Bingo. This was what happened to it?
It's back on again.
This was an easy port. Okay, so Atari didn't make up this game. Sorry, not Atari. Coin-Op made this game. I don't even. Oh, it was one of ours. Namco originally, but it was really easy. So, for example, you see this big bunch of things. Most of those are graphics characters, not moving objects that move. And then if you were going to make one of them peel off and come on down, you would replace that. You would erase the graphics character and replace it with the moving object version. And then it could break loose and come in and shoot you, right? And we had lots of control over the color, and I think that we were actually still changing colors on the side as we went down. One more game before I go do something else. Donkey Kong. Donkey Kong it is. Right. Now, I don't have sound, so it's not going to be interesting, but I just wanted you to see that it was quite straightforward to port this game from the 1977 video game world to this machine. That's the point of this discussion. All right. One of the things I'm thinking of doing for the book, and that is, first of all, to reference how common emulators work, how to get joystick equivalents on USB, and how to port some game, either a common one, here's how I would design it, or even go better. How many of you saw last year the movie Wreck-It Ralph?
Yep.
Many of you. Good. I was thinking, it's probably too much work, but I was thinking, could I compose Fix-It Felix and write it for this machine and then put the listing, or at least the design, in the book? I'm thinking about that. Okay? The best original game on this machine was Star Raiders, written by Doug Neubauer, who also built one of the chips. And I was wishing I could talk him coming here, because Star Raiders was so good that Atari management decided to go back, and instead of making a keyboard an add-on for the 400, they built it in. It was too important because this thing uses keyboards extensively.
Okay, can you come to the registration desk? We have one.
All right. I'm not sure how many slides I've got left. Let's find out. 35 of 42. This is going to be tough. All right. On the other hand, if you fail to get up and leave, then we'll be where we are. All right. Gonna have to make this fast. All right. We had BASIC. Bill Gates said, here's BASIC 12K. And so we hired somebody else, Shepherdson Microsystems, to do a 4K version, assuming that we could put 2K of floating point in the operating system itself. So that was really a 10K versus Bill Gates, but there we were. Many different companies produce 6502 self-assemblers. OSS also ships Tiny C, so you could get C for this thing. OSS built something special called Action, which was a game-oriented set of APIs for the hardware. Forth was available from Atari Program Exchange and a couple other companies. You could get Logo for it. You could get Lisp for it. Some of you even remember what Lisp was. The development environment was, I could build a complete system with this, and I could port stuff for it on it with assemblers and whatnot. The system documentation was superb. Atari published huge bunches of manuals. This is actually the source code listing of the main OS built in. There you are. Okay? And Atari Programming Exchange produced this fantastic book called Day Ray Atari. This is now available on the web, because I don't know if you can buy these anymore. But this is a terrific how to program this system book. Yeah, self-assemblers, there's Action T. You could write. So, let's suppose you're a software developer and you want to write stuff for this. Now, out there on the floor, there are people who are probably writing proms of some kind for those Atari 2600 cartridges they're still selling. What do you do here? One of them is you can write things to a floppy. That's nice and easy, except your target market isn't very large because they have to spend so much money to get these things in the first place. The market's kind of small. But with tools like the Thomson Electronics prom burner that fits in the right side socket, you could burn EPROMs and then go off and get mass ROMs made from those EPROMs and sell them to a larger market. We were trying to enable developers. Obviously, as they went on, Atari decided to repackage the same chipset as a dedicated game machine. Now, all this mass up here is that they wanted to be able to store the controllers in here to reduce the amount of clutter in someone's living room. But it was too late to save Atari from the general collapse of the video game business that happened between 1982 and 1984. So, lessons learned and not learned. All right. As a game console company, we again thought that we needed to provide good self-development tools to attract developers to build an ecosystem. And the founders of Activision and Magic hadn't left yet, so Atari wasn't afraid of them. That happened later. Okay, as a computer, we thought we needed to be able to do massive cost reduction. I mean, the 800 XL here probably cost us no more than half of what it cost us to build that original machine. We built cost-reduced disk drives, but they had on the drawing boards machines that integrated this with a built-in floppy that would have been much more cost-effective, but they were too late to save the company. And we really wanted to have an expansion unit with slots, and we never could. So our concepts for our third system were, we wanted to be able to do cartoon-level animation. Of course, at that time in history, a VCR, played the VHS tapes, was itself pretty expensive. It would cost, $300-400 in 1982 dollars. And we wanted to build a machine that people would buy, and we wanted programmers to be able to do interactive cartoons in 1982. That was our concept. Larry Kaplan of Activision precipitated this project, but he didn't actually participate. We wanted to do cartoons. We actually figured out how we would make little Smurfs move around and do things. We wanted to accelerate bitmap manipulation in hardware. So this thing had the first bit blurs. This thing could take an image and an image of a Smurf and the outline of the Smurf and cut and paste them together and make a new bitmap image in the time it took to read and write the bytes. It was that fast. It could touch every single pixel in a 60th of a second. I had testified in a patent case involving it 10 years ago. It's still around. And we wanted to synchronize with external video. So one of the Amiga features is that it had an extra connector and it could synchronize its video with an external video source. So for a very long time there was a product called the Video Toaster that you could buy as an add-on to the Amiga. And this was used for, you get, the weather asshole standing in front of a green screen and he's doing this and that and the other thing, and then they've got the weather map projected separately and, generated by an Amiga, and you could put them all together and make one shot. These were in video production systems for 20 years. as a computer, we wanted 80 columns, and it did 80 columns on monitors. We wanted enough bitmap memory for a Windows-like OS, and in fact, the first Amiga OS was one of those. It had 128K bytes of RAM to start. It had a built-in 3.5-inch floppy, and the hardware was designed to talk to external hard drives. So that's what it looked like. And again, I suggest, where'd it go? The sequel to the book I want to write is called The Future Was Here, and that's described there. And so, all I've got here is resources. I'm giving these slides to Rick Weiss, who's running this thing, so if you don't get them from me soon, you can get them from him later. Find those things and read them. I don't think I have much more time for questions here, but maybe offline. They want to kick me out, I think. It's actually 1:30 on the nose. Glad to please.